Welcome to The Explainer. So today, we're tackling what is arguably the real hero behind modern AI. We're talking about a fundamental algorithm in machine learning called gradient descent. Whenever a model learns from its mistakes and actually gets smarter, gradient descent is almost always that tireless engine running under the hood. It's basically the ultimate navigation tool, an optimization algorithm that helps our models lock in the absolute best weights by gradually squashing down their errors.
Okay, let's dive into this. Don't worry if the math sounds intimidating because we're going to walk through a really comforting roadmap here. First, we'll frame the core machine learning problem. Then, we'll take a little walk down a foggy hill. Next, we'll define what a gradient actually is, unpack the step-by-step process, and finally, look at the weight update equation. Right, section 1, the machine learning problem and finding those optimal weights. So as a quick refresher, during the training phase, models learn by adjusting their weights, which are sometimes called parameters. Think about a model built to predict house prices. A brand new model knows absolutely nothing, literally zero. It starts out with completely random weights. And because these weights are essentially wild in-the-dark guesses, its initial predictions are just terrible. I'm talking massively high prediction errors. So we start out way over on the left in a super high error state with random weights. The entire objective of training is to cross that chasm over to the optimal state where we hit minimum error. We literally just have to continuously adjust those weights until the prediction error, mathematically, bottoms out. But how on earth do we make those adjustments? Well, gradient descent automatically tackles this huge task by repeatedly asking one incredibly simple, fundamental question. Should the weights be increased or decreased to reduce the prediction error? By making tiny, calculated corrections in every single iteration, the algorithm steadily steers the model toward the best possible set of weights. Which brings us to section 2, walking the foggy hill. Let's use a physical analogy to really ground these highly abstract concepts we're exploring. Picture this. You are standing on a steep hill and you're surrounded by incredibly thick fog. Your one goal is to reach the lowest point of the valley, but because the fog is so dense, you can't see the landscape around you. You can't just plot a straight line to the bottom. So what do? You look right down at the ground near your feet, figure out which direction slopes downward, and you take a small, careful step. Then you check the slope again, and you take another step. You just keep walking downhill, step by step, feeling the ground each time until you eventually hit the flat valley floor. And this brilliantly illustrates how gradient descent actually works. The two journeys perfectly mirror each other. The physical hill, that represents the model's loss function. Your current position in the fog is the current weights. The bottom of the valley is your minimum error. That downward slope dictates exactly which direction reduces the error, and those small steps you take represent the weight updates. So instead of just wildly guessing, the model intelligently follows the downward slope. Moving right along to section 3, what is a gradient? We've got the physical intuition down, so let's introduce the formal mechanism that drives this whole thing. Simply put, a gradient is just the slope of the loss function. In math terms, you'll see it written as dl over dw. The absolutely crucial thing to remember here is that the gradient acts as our guide. It tells us exactly how much the error changes based on the weights, and specifically in which direction we need to go to reduce that error. It has this opposing nature, which is actually super cool. A positive gradient means the error goes up as the weight goes up, right? So to fix that and reduce the error, we actually have to decrease the weight. On the flip side, a negative gradient tells us the exact opposite. We need to increase the weight. And what if the gradient is 0? Well, that means the minimum error has been reached. The ground is perfectly flat. Now keep this in mind. Mathematically, a gradient always points toward the direction of the steepest increase in error. That is exactly why it gets its name. We want to descend. The algorithm intentionally moves in the total opposite direction of the gradient to shrink that error. Let's check out section 4, the step-by-step process of how the model learns. This is the actual looping mechanism, and I want you to really feel the rhythm of this because the machine is doing this incredibly fast. Ready? Step 1, initialize random weights. Step 2, make predictions. Step 3, calculate the error. Step 4, compute the gradient. Step 5, update the weights. And step 6, repeat. It just loops and loops endlessly until the error is tiny or it hits a limit. With every single cycle, it's learning and getting more and more accurate. Let's move to and see how this builds into section 5, The weight update equation. We are at the mathematical climax here.
We've done the analogy, we've done the rhythm and steps. Here is the actual equation that makes all the magic happen. W new equals W old minus eta times DL over DW. Take a breath and let that sink in for a second. This equation is simply the literal mathematical version of that foggy hill story you just heard.
Now, what's really interesting about this is how perfectly these variables map out your journey. W old is just your current spot on the hill. W new is your position after you take a step. L is the hill itself, and DL over DW is the slope. And eta, that's the learning rate, literally the size of the step you take. By subtracting the gradient multiplied by that learning rate, we literally force the current weight to step in the precise direction that cuts down the loss.
Gradient descent shows us you really don't need a perfect map to reach your destination. You just need to know your current error, check your slope, and be willing to take a small step in the right direction, over and over again. So I'll leave you with this. How many small, iterative steps will it take to reach the minimum error in your own learning journey? Keep taking those steps, keep updating your weights, and thank you so much for joining me on this explainer.